All right, let's finish up Module 1, the end of Chapter 1, Section 1.5. Okay, so after this, you'll be good for all of Module 1. So get all of your assignments, all of your quizzes done, and let's rock and roll. So here we go. For Module 1, Section 1.5, I've given you some notes, and they are how to find domain of functions when given the equation, because we have found the domain of functions when given a set, when given a graph, and then now we're going to complete that with finding the domain of a function when given an equation. We're not going to worry about range for this, okay? We just want to find the equation, okay? Or find the domain using the equation, I should say. And then down below that, I have given you the types of functions and their equations that you need to know, okay? So these are the types of functions and different equations that we deal with, okay? So let's first start off with finding domain of equations. So I've got this equation here, okay? So in order to find the domain of this, I have steps right here for you to follow, or technically like 2 steps. 1, for that equation, we're going to assume that the domain is all reals to begin with. Okay? So right now, this domain is all reals. And then if you look at this, unless we have one of these 2 situations. So our domain is all reals unless it is a rational, where it looks like a fraction. Okay, variables in the denominator is what makes a real rational. Or in other words, it looks like a polynomial over a polynomial, like an equation over an equation. Okay, so if it looks like a fraction with a variable in the denominator, you have a rational. Okay, and that changes our domain. Or it looks like a root function. Okay, where you have like a square root or a cube root, a fourth root, whatever. So it's got some sort of root over your equation. Okay, these 2 mess up our domain, rationals and roots. Okay, so in the beginning, your domain is all reals unless this thing is rational or a root. Well, what does this look like? It looks like a fraction. So that means we have a rational. Plus, you see that variable in the denominator. So when you have a rational, here's what you're going to do. You're going to set the denominator equal to 0 and solve. Okay? The reason why we set our denominator equal to 0 is because whenever you have a rational or a fraction, if you take a number divided by 0 in the calculator, your calculator will give you an error. Okay? Just to show you, let's bring up the calculator for this class. So it's loading. But if you take a number divided by 0 in the calculator, it will give you an error. Okay? See, look. 8 divided by 0. Doesn't matter what the numerator is. See? Error. Divide by 0. We cannot divide by 0. That's bad news bears. So that is why we set the denominator equal to 0, because we are finding the numbers that make 0 down here. Okay? So we come back here. We're going to take x minus 2, set it equal to 0. We don't care about the numerator. The numerator can do whatever it wants. We just care about the denominator. So set the denominator equal to 0, add 2. X is equal to 2. So if I plugged in 2 up here, 2 minus 2, that gives me 0. This is a bad number. So how we write this up with domain, showing you both set and interval. So this is the number that we don't like. We like any other number but 2. Okay? 3 is cool. 10 is cool. Negative 100 is cool. Negative 0.2222222 repeating is cool. Okay? Any number but this guy. So how we write that up in set notation, I tell you it looks like this. All you're going to do is put your X, your line, in other words, your embellishments, and then you're just going to put a slash through the equal sign from when you solved. Okay? So I'm going to put my little embellishments. And if the variable was something else, I would put that variable in here. So if it was Y, I would put Y. If it was Z, I would put Z. And all I'm going to do is take this piece right there, rewrite it with a slash through the equal sign. And boom, there's set notation. Interval notation. Now remember, we like every number but this guy. So it's like I'm going to have a party, and I'm going to invite everybody to the party but 2. 2 is not invited. 2 is like that friend, you're sloppy drunk that you have to end up watching all night and then taking care of because they're in the bathroom puking in the toilet. That's what 2 is like. Do you really want to invite that friend to the party where you have to babysit? No, you want to have a good time. So if we do interval is going to look like this. Basically, you're going to start at negative infinity, and you're going to go up to the number we don't like, and you're going to put a parenthesis. And I usually call this parenthesis union parenthesis because we're going to jump over the number we don't like. Okay? So this parenthesis union parenthesis means that we're going to jump over our number, and then we're going to pick up on the other side and go on to infinity. Because remember, we like every number but this guy. Okay? So we're going to start at negative infinity, get to our number, jump over it, and pick up on the other side of our number to infinity. So this answer looks like negative infinity, go up to our number, which is 2, jump over it. Parenthesis, union, parenthesis. Pick up on the other side of 2 and go to infinity. And there is interval notation. Super easy. You need to make sure that you know how to do both. This is kind of like an OR answer that you've seen before, although in ORs you usually have 2 different numbers here. Okay? All right. Then there's this one. Right now, our domain is all reals. Unless it looks like a rational, which it's not. But does it look like a root? Absolutely. It's got that square root on it. So when it comes to roots, you're going to take whatever's under the radical and set it greater than or equal to 0. And you're going to solve. Reason why we set it greater than or equal to 0 is because I can take the square root of 0, of 1, of 2.6. We can do all of those. But if I try to take the square root of negative 1, or square root of a negative 2, or the square root of a negative 7.8, our calculator does not like these. Let's take a look real quick. So second x squared, there's your root key, negative 1. Just push that. Hit enter. See? Error. It says non-real answers. You'll learn about that coming up in section 5.6. Okay? All right. So we're going to set the polynomial under here greater than or equal to 0. And we actually like these numbers. Whatever happens here, whatever happens with the answer after you solve, that is what we're going to actually put in the set notation. Okay? So we like these answers, but we do not like the rational ones. Okay? We have to throw those out. All right. So we're going to come back to our problem, and all we're going to do is take this 6 minus 2x and set it greater than or equal to 0 and solve. And once we solve this, these are the answers we're going to like. So again, these over here, just to remind you, error. We can do these, but we cannot do those. All right, so let's solve. So we're going to subtract 6. Negative 2x is greater than or equal to negative 6. Divide by negative 2, divide by negative 2. Negative 6 divided by negative 2 is a positive 3. And in this guy, remember, here it is again. When that denominator is negative, flip the sign. And there we go. All we got to do is write up our answers. So set will look like this. Parenthesis or bracket braces x line, and then you just plug that answer in. X less than or equal to 3, and then close it. There's your set. Easy peasy. Interval. You've done this before. Just write this in interval notation. And what's cool about it is it'll either take one of these two forms. So if you have the less than, it'll be negative infinity to your number and a brace and a bracket. If it's greater than, it'd be the bracket your number off to positive infinity. It's one of these two. Okay? So if I come back and look at this, it's the less than. So that means I'm going to start at negative infinity, and I'm going to go up to 3 bracket. And there you go. There's our domain for this function. Okay? Again, if you are not a root and not a rational, your domain is always all reals. Okay? All right. So give these 3 a shot on your own. Pause the video and go. Find me the domain. All right. So hopefully you recognize this first one as a root. So all you had to do was take the 6x plus 3, set it greater than or equal to 0. And then solve. Minus 3, minus 3. 6x is greater than or equal to negative 3. Divide by 6, divide by 6. X is greater than or equal to negative 1/2. So if we write up our answers, the set notation, your embellishments, and then all you do is you put this inside the set. X greater than or equal to negative 1/2. There's the set. Interval notation would look like this. Since it's greater than, it will start at our number with a bracket. So bracket negative 1/2, and then shoot off to infinity. There's your interval. There's the domain for g of x. Okay? Right over here, hopefully you recognize this as the rational. So all we have to do is set our denominator equal to 0. So we'll subtract 10. So 2x is equal to negative 10. Divide by 2, divide by 2. We find out that x is equal to negative 5, and this is the number we're going to throw out. We do not like negative 5. We like everybody else but negative 5. Remember, don't touch the numerator. The numerator's fine the way it is. It's all about the denominator for rationals. Okay? So our set answer for domain would look like this. Basically, rewrite this, and all you're going to do is put a slash through the equal sign. Interval notation, we like every number, so that means we start at negative infinity. We'll go up to the no number, and then we're going to jump over it, picking right back up on the other side and shooting off to infinity. And there is the domain for h of x. Last but not least, if you look at this guy, this is neither a rational nor a radical, a root. So that means this guy always had the domain of all reals. So there's the interval, because you know how to do all real domains. And if you, the set is just all real numbers. And there you go. Yeah, there's nothing special about this. Its domain is all reals because it's not a rational and it's not a radical. Okay? All good. So there we go. There is domain from an equation. I want to change the color of this stuff. There we go. Let's make it blue. That's much better. All right. So functions. You've been looking at function notation in here. So that G with the parenthesis X, the H with the parenthesis X, the F with the parenthesis X. Same thing back here, that H of X and F of X. Okay. So let's talk about what functions are. Functions are kind of a way for us to, as mathematicians, shorthand write some information. Okay. So functions, you're going to see that notation. And again, you know that they can change the variable. We like H of X and G of X. Most of the time we'll use F of X. Okay. But that variable can change to whatever it wants. Okay. How you pronounce this is like what you've been hearing me saying, F of X. Or this guy is H of X, G of X. But really what it's saying in the end is that this is a function of X. Hence why they like to use F a lot, because we talk about it as a function. Okay? So this means this is a function of X. If it was a different variable in here, say all these variables were A, then we would say this is F of A. And say that it is a function of A. Okay? So know that these variables can change. Okay? But it always reads the same. Now, what is a function? Why do we call these a function? Okay? Reason being is because of this. Functions. Every x value has one and only one y value. Okay? A function means that every x value in here is going to one and only one y value. You've heard that before. Okay? I know you have. You've heard it in algebra. You've heard it in algebra 2 or some other class that you've had math in. You talk about functions all the time. Okay? Every x value has one and only one y value. In other words, what I'm saying is x's don't cheat. Okay? The x's go to one and only one y. X's don't cheat. Or in other words, x's should not repeat. If the x's repeat, it's not a function. So what we're going to do is we're going to look at sets. We're going to look at a table. We're going to look at, I guess you could call them input-output tables with arrows. And we're going to look at graphs and determine if they are functions or not. It's really, really easy. X's don't cheat. X's do not repeat. Okay? So, here is set notation. Is this a function? Well, all you have to do is look at the x's. We don't care about the y values. Just look at the x's. All those x values are different. There is not a repeat of x. So that means, yes, this is a function. Plain and simple. There you go. X's don't cheat. Every x value has one and only one y value it goes to. Okay? Pause your video. Tell me if this is a function or not. Okay. So if you look at the x values, you got 1, -3, -2, -3. Wait a minute. I said -3 twice. So hopefully you said no to this. This is not a function. Why? Because the negative 3's repeat as an x value. Okay? Notice I have a negative 2 as an x and a negative 2 as a y. That don't matter. It's all about the x's. And x's don't cheat to be a function. All right, take a look at this. Is this a function? Go. Okay. So hopefully in this one you said that, yes, this is a function. Again, it's okay that y is all 5. There's nothing wrong with that. Y's can cheat. They can do all they want. They can cheat all they want. But your x's do not cheat. Notice there is a different x here. 1, 2, 3, 4. None of them are repeating. That's a-okay. Okay? This is a function, even though all the y values are 5. There ain't nothing wrong with that. Y can do whatever it wants. It's the x's you have to pay attention to. And again, all this is, the table, is just taking like these points and putting them into a table that is x and y. So giving you sets earlier versus the table, there's no difference. You're just looking at the x's. See? All of these are different. As long as these are all different, it's a function. Okay? All right. Take a look at this input-output table. Is this a function? Go. Okay. So hopefully you said, yes, this is a function. Because every x value is going to one and only one y value. See, there's only one arrow there. Negative 8 is going to 100. 0 is going to negative 11. Negative 10 is going to negative 7. 23 is going to 100. Yes, 100 has 2 people coming to them, but that's okay. Outputs, y variables. Okay, this is the y column. Y values can cheat. The x's cannot. Every x only has one arrow coming from it. Now, if I went back in and did this, then now this would not be a function. Why? Because negative 8 thinks it can get away with going with negative 7 and 100. Now negative 8 is cheating. And if we wrote these out as points, you would see negative 8 appear twice as an x value. Okay? So, just so you know, x's don't cheat. Okay? All right. But overall, yes, that is a function. Okay. Now let's talk graphs. So if I give you a graph like this, a line, how do I know if this is a function or not? Because obviously it's not listing out the x values or the y value, or well, it's not even giving me any points or anything. It's not telling me inputs. It's not telling me outputs. All I got is this blue line. Well, lucky for you, we have what is called the vertical line test. And here's what the vertical line test says. Vertical line test. You're going to draw in lots of vertical lines. Hence why we call it the vertical line test. If a vertical line intersects the graph 2 or more times, it is not a function. Because the moment the vertical line intersects the graph twice, that means that x value is cheating. Okay? So if I come up here and I draw in a ton of vertical lines. Let's just grab this guy. That's not very vertical. There we go. And then I draw on a lot more. Okay? As many as you want, as long as you want. Just keep drawing in vertical lines. Oops. So, if I look at all these vertical lines, how many times did each one of them hit my graph? Only once. One time, 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 one time. So all these vertical lines hit my graph only once. Is there anywhere where I can hit it more than once? No. So is this guy a function? Yes. This is a function. Okay? So we use vertical line tests for graphs. As long as my vertical lines only hit the graph once, we're good to go. All right. What about this guy? Pause the video. Go. Okay. So hopefully you're drawing in vertical lines. And that didn't work so well. Vertical, 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 vertical. Whee! That's not so vertical. This guy. Vertical. So, how many times are my vertical lines hitting my graph? Only once. So is this a function? Absolutely. Okay? So here are 3 graphs. Go ahead, try it on your own. Tell me if they are functions or not. Go. Okay. So, if we draw in lots of vertical lines here, and then I'm just going to go ahead and do this for the other graphs. That's not so vertical, Mr. Armstrong. There we go. I don't want to move my picture. Come on now. Vertical lines, lots of fun. All right. So as we look through this, is A a function? Absolutely. All those vertical lines only hit the function once. And B, is that a function? Absolutely. All those vertical lines are hitting the function only one time. Is C a function? No. I have 3 vertical lines here that are hitting it more than once. See? 1, 2. 1, 2. 1, 2. Technically, I could have stopped after 1 vertical line because the moment you hit it more than once, you're done. It's not a function. No need to keep drawing stuff on there. Okay? But you can see the vertical line test working. This is not a function. Circles are not a function. Okay? And there you go. Easy peasy. All right. So, near the end of this, basically all you're going to be doing is evaluating. That's what they want. So, function notation helps us as mathematicians to evaluate really quickly in right directions because all we're going to say is evaluate. And what they want you to do is remember what was right here in that spot. There was an X. So all they are telling you to do is plug in -1 and evaluate. Okay? So all they want you to do is take this -1 and plug it into every X that you see over here and tell me what the answer is. Because this part right here used to be the variable X, and now there's a number in it. So they're saying plug in -1 for X. Okay. Whereas if I was going to write this out, usually the directions would look like this. If X equals -1, then oh gosh, find the Y value. And me as a mathematician, I want to write that every time. So I can just say evaluate and give you the function notation, and that represents everything that I just said here. Okay? So I don't have to write this out. I can use function notation to help me deliver those same directions. Go ahead and make this a capital I. So all they're wanting you to do is take this and plug it in. So let's do that. So if I take the -1 and plug it in, f of -1 equals 3, oh, I see an x, so that's negative 1 squared, plus 2, oh, I see an x, so that's negative 1 minus 10. And then you just perform a little bit of PEMDAS. So be careful with your PEMDAS here. Okay? So negative 1 squared, because you take care of squaring first, is a positive 1. And then PEMDAS says take care of multiplication and division. So 3 times 1 is 3. 2 times negative 1 is negative 2. And then you take care of adding and subtracting from left to right. So 3 minus 2 is 1. 1 minus 10, negative 9. And that's what they're looking for. So f of negative 1 equals negative 9. So when x is negative 1, the y value is negative 9. Oh, I meant to tell you that. Back here, just so you know, f of x in function notation, this is a fancy way of also just saying y equals. So if you don't like using the function notation, you can change it out for y. There's nothing wrong with that. Okay? F of x, y equals, they are the same thing for us. Okay? All right. Getting back down to where we were at. So all they wanted you to do was plug in. Let's take a look at another one. Now look at this one. Well, there's no number in here for x, so we're not plugging into x, but it says f of x equals 10. Well, remember what I just said. F of x is a fancy way of saying y equals. So another way of saying this is they're telling you that y is equal to 10. They want you to find the x value. That's what they want to know. So if y is 10, what is x? So we're going to take the 10 and we're going to plug it in, because remember, this is where the y variable is. So we're going to say 10 equals 5 plus 15x. And now solve for x. So minus 5, so we get 5 equals 15x. Divide by 15, divide by 15. X is equal to, and then when this reduces down, 1/3. And that's what they're looking for the x value. That's all they wanted. So if a number is inside the parentheses, that's x. If you got function notation equal to a number, they're telling you the y value. Okay? All right, pause your video and give these a shot. Just so you know, these are two separate problems. So f of 2, f of negative 1, go with the above. F of x equals negative x squared plus 2x minus 7. And then the f of x equal to 13 only goes with the f of x equal to x minus 7. And go. All right. So what are they giving you here? They're telling you x. So all you got to do is take the 2 and plug it in. Now, be careful on this, because this negative is not with that x. Technically, what's going on right here, this is negative 1 times x squared. So hopefully you were observant on that. You got to be careful. So that's negative 1 times 2 squared, because x is 2, plus 2 times 2 minus 7. So 2 squared is 2. And then negative 1 times 2 is negative 2. 2 times 2 is 4 minus 7. Okay? So negative 2 plus 4 is 2. 2 minus 7 is negative 5. And there you go. Down below that, so we got negative 1 times negative 1 squared, because this negative 1 is because of the x value there. That's x. Plus 2 times negative 1 minus 7. All right. So PEMDAS says squaring. So -1 squared is 1. So that's -1 times 1 plus 2 times -1 minus 7. -1 times 1 is -1 plus 2 times -1 is -2. So I'll just say that's -2. And then minus 7. So -1 minus 2 is -3. -3 minus 7 is -10. And there you go. Just plugging in. That's all they wanted you to do over on this side. Over here, now they are telling you the y variable. They're telling you y is 13. So you're going to take the 13 and you're going to put it in the y spot because this is y equal to x minus 7 and solve for x. So plus 7 plus 7, x is equal to 20. And there's the answer. That's evaluating. They just want you to plug in. Easy peasy lemon squeezy. All right. They will also want you to be able to evaluate from a graph. Okay, so I've given you a graph here. Let's do some evaluating. So again, right here, they're telling you what x is. So they're saying x is 1. They want to know what is the y value. Okay, think of this as a point. They're telling you x is 1, comma, what for y. So if I go out here and I find x is 1, here's where x is 1. What's the y value on the graph? Oh, it's right here. It's at -3. So the answer to this is -3. Because that's where the graph is at. 1, comma, -3. That's all that you're doing on this, is you're basically using the graph. Think about which variable you got. So if I look at the next guy, again, they're giving me x. They want to know the y value. So they're saying x is -3. What's y? So if I go over here, 1, 2, 3, here's -3. What's the y value? It's up here at that line, which is +3. And there you go. See, nothing crazy. And then last but not least, if you look at this, they are telling you the y value. So they want to know what x is. Okay? Now you got to be careful on this one. So we know the y value of -3 is right here. So we definitely know that an x value is 1. So we know x is equal to 1. But if you look back the other direction, oh my gosh, there's another place. What is that x value? Well, that's 1, 2, 3, 4, 5. It's at a -6. So when you're dealing with the y value, it is possible that you might have more than one answer. You got to look across the y value and see if there's more than one place where your graph exists. And our graph existed in 2 places. It existed where x is 1. It also existed where x is -6. So you got to make sure that you put those. So when it comes to finding the y values, there's only going to be one answer because it's a function. Okay? When it comes to finding the x values, you might have more than one answer because the y's can cheat. Okay? So in our case, we had 1 and -6. All right. Last but not least, deals with the second part of our notes. Okay? They're either going to give you the name of a function and they want you to identify the graph, or they will give you a graph of the function and they want you to identify the name. Okay? So for instance, right here, this says, which graph is the cubic graph? Okay? Only one of these is the real cubic. So you got to be able to pick it out. That's why I've given you this picture. Okay? So here's the cubic graph. Notice it starts down and then swoops up. I need a picture that looks like that. So if I come back, nope, that's sideways. No, that starts out or up and then goes down. Sideways. Oh, it's this guy. See how it starts down and then swoops up? So I know you'll have a question like that. Here's the function. And then they say which one below is the graph of it. Okay? Or they'll do this. What is this function? So here's a picture. What is it? So if you go back to your list and I scroll down, oh, there it is. Here's the one that looks like a V. They call it the absolute value. So absolute value. And there you go. Dunsies. And that, my friends, is the end of Module 1. That is Section 1.5. Catch you on the flip side.